When we make electronics, like CPUs or RAM, we design them with some kind of plan to eventually take all these separate parts, put them together, and make a computer. Evolution had no such plan, and yet the brain computes. How does computation arise without explicit design? This idea is one from 1982, and was also part of one of the first big breakthroughs in understanding neural networks. This video is the first in a series I'm starting where we will examine foundational breakthroughs in AI architecture chronologically through time, and each video in the series will be grounded in a specific paper. The paper for today's video was written in 1982 by John J. Hopfield, titled Neural Networks and Physical Systems with Emergent Collective Computational Abilities. Before we get into the paper, it would be helpful to have some context. For one, we should understand the basic idea of a neural network, a collection of simple units connected by weighted interactions. If you've never heard of neural networks before, it might be helpful to watch my short introduction to neural networks first. Another thing we'll need to know is what emergence means in this context. A professor of mine described emergence as follows. An emergent property is one present in the whole, but not in any of the parts. For example, ant colonies lay pheromones, and because of this, they always end up taking the fastest path to their destination. No single ant is able to find the fastest path alone, but together the ants find the fastest path. Another example of this is in us humans. Through interactions of humans, new things are created, like economic markets, corporations, persistent culture, and so on. The ants are an example of weak emergence, and the humans are an example of strong emergence, an important philosophical distinction, but one that's out of scope for the video. We've already understood everything we need in order to get to Hopfield's paper. In 1982, when Hopfield presented this paper, AI was dominated by explicitly designed algorithms and symbolic reasoning. This meant that computation was primarily understood as a step-by-step procedure, with symbols, rules, and explicit control flow, designed by a human engineer. Neural networks existed, but were not seen as principled computational systems. Hopfield explicitly challenges this view with the central claim of his paper. Large collections of simple, locally interacting units, for example neural networks, can exhibit stable, interpretable, computational behavior as a global property of the system without any centralized control structures. This is a strong claim, and it's essentially the entire motivation behind neural networks. Don't worry if you don't understand it, that's what this entire video is about. To argue this claim, Hopfield presents a specific architecture, which now in 2026 we call the Hopfield Network. The Hopfield Network is intentionally a very simplistic network. Its components are simple and its rules are local. I'll now present some key features of the architecture. For one, neurons are binary. Each neuron has a simple state, active or inactive, either firing or not firing. For weights are symmetric and bidirectional, meaning the connecting weights between neurons act in both directions with equal strength. The network is fully connected. Each neuron is connected to all other neurons. Neurons are not connected with themselves. In other words, there are no self-connections. Neuron states are updated with a rule based on weighted input from other neurons. The exact rule is not essential, but what matters is that it depends on local information. This rule is localist. And for learning, or the weight update rule, weights are updated with a Hebbian-style learning rule. A nice phrase for Hebbian learning is that neurons that fire together wire together. Essentially, if two neurons are both active at the same time, the connection between them will strengthen. And then there's the operation of the network, or inference. When presenting input to the network, neuron state updates are asynchronous. There is no single time step where all neurons are updated. Instead, at each time step, a neuron is selected at random and the update rule is applied. At the time of operation, the weights have been learned, so weights are fixed. And before operation, there's the learning phase. Input patterns are presented to the network in batches, and the weights are adjusted according to the rule. The important point here is not biological realism, but that this system consists of many simple units interacting locally, with no explicitly designed central control structure. Now Hopfield takes this network and frames it as a dynamical system. What that means is the entire network can be represented with a global state, specifically a vector, where each dimension is the state of each neuron. The value of each neuron is what defines the global state. As neurons receive input and update according to the rules, the global state changes. To understand why this actually matters, we need to understand this idea of states a little deeper. For every possible global state of the network, the update rule determines what happens next. In this sense, each fixed set of weights implicitly defines a set of possible states that the network can be in. We call this the state space, and we can think about it like kind of a landscape. And we can model a specific state of the network as a specific point in that state space. Most of the states the network can be in are unstable, meaning at least one neuron's current value is misaligned with the input it receives from its neighbors, so the update rule will force a change. And when a neuron updates, the global state changes. That change can cause other neurons to become misaligned with their inputs, triggering cascading updates. However, some states are special. There exist certain states in which no neurons are driven to update. In other words, all neurons are already in agreement with the update rule. In this case, no neurons will update, and the global state will remain unchanged. This is called a stable state. Once the system is in a stable state, it stays there unless it's externally acted upon. What Hopfield shows is that not only is the network capable of remaining in stable states, but the network will naturally move towards those stable states. Starting from an initial configuration, the local update rules will cause neurons to change their values through multiple time steps, eventually settling into a state where no further changes occur. This behavior of cascading updates is the system traversing its state space. When we present an input pattern to this network, we are essentially initializing the system at a specific point in state space. In the language of dynamical systems, these stable states are called attractors, because the dynamical system is attracted to these states. The weights define the geometry of the state space, while neuron updates define motion within that space. Under this view, computation is not a sequence of symbolic steps, but the relaxation of a dynamical system into a stable configuration. At this point, we've roughly seen the Hopfield network as a well-defined system with stable states. This is a really profound idea presented by Hopfield, but it's not immediately clear how this system performs any meaningful computation. To think about that, let's look at some of the consequences of this dynamical systems framing. Hopfield demonstrates that this system exhibits emergent properties, most notably content-addressable memory. Before looking at how this appears in the network, let's clarify what it is. Content-addressable memory, also known as associative memory, retrieves a memory on the basis of sufficient partial information. Take, for example, a content-addressable memory system with the memory, "I bought an apple yesterday." If we present the partial information, an apple, to the system, it would be able to retrieve the memory. In the Hopfield network, the stable states or attractor states are actually the memories of the network. Like we saw earlier, when the network is given partial input, that input puts the system near one of these attractors in state space. From there, the dynamics of the network do the rest, pulling the system towards the closest attractor, or memory. In this way, retrieving a memory is a process of the network converging onto this stable state, rather than a traditional lookup operation. But you're probably thinking, why do memories become attractor states? What makes these patterns special? Well, this happens during learning, and it's a consequence of the Hebbian-style learning rule we mentioned earlier. Patterns the network is exposed to become self-reinforcing. What that means is, during learning, when a particular pattern is presented to the network as input, weights between coactive neurons become strengthened. These coactive neurons are the ones that are representing this pattern. And as we saw earlier, the weights define the geometry of the state space. So, during learning, the inputs reshape the state space so that these patterns become stable. If the network enters a state that partially resembles a stored pattern, the local update rules push it towards completing that pattern. This state that the network settles into is the memory. Crucially, the memory is not stored or represented in any one neuron. It is distributed across the entire network, a distributed representation of a memory. This idea will come up later. Now that we've understood this framing of memory, the other emergent capabilities of the network follow naturally. The network can perform a kind of generalization. When presented with noisy input, the network will drift towards the nearest known stable states. It can even perform categorization. Different inputs that share common structure will collapse to the same attractor. This is also a form of error correction, because incorrect activity is overridden by the collective influence of the rest of the pattern. What's crucial here is that there are no separate mechanisms for these behaviors. They're all consequences of the same dynamics. Hopfield's paper marks a turning point in how we thought about computation in intelligent systems. Before this, computation was the product of external design. If a system was doing any meaningful computation, it needed a designer to specify the representation, the sequencing, and control structures. Hopfield showed that computation could instead arise from the internal dynamics of a system. Very importantly, this is an architectural claim. Hopfield's system does not build behavior with separate mechanisms. Instead, a single fixed architecture constrains and defines the computation, in which the behaviors emerge through the system's dynamics. This is completely unlike traditional programming, where we decompose intelligent behavior into isolated modules. And this doesn't mean that the Hopfield network has solved intelligence, and it doesn't mean that all possible cognition lies within dynamical systems. But it establishes a foundational idea that the modern AI space relies on today. Architecture matters because it defines the space of possible computations. At the same time, this paper leaves an important question open. Hopfield showed that these systems exist in states, but he says very little about the internal structure of these states. How could any semantic meaning come about from these states? How does a state represent anything? Answering this question requires engaging with the idea of distributed representations, where meaning is encoded by mathematical structure. That shift is the focus of the next major step in AI architecture. In my next video, we'll look at parallel distributed processing, the work that formalized distributed representations and showed how semantics and abstraction can emerge from neural activity. Here we just saw how architecture gives rise to computation. In the next video, we'll talk about how architecture gives rise to representation. Thanks for watching my video. See you guys in the next one.